If you were standing at arm's length from another person, just a normal distance, and each of you had just 1% more electrons than protons in your body, just 1 tiny percent of imbalance, the repelling force between you two would be enough to lift the weight equal to the entire Earth. Not a building, not a mountain, the whole planet. That's how ridiculously strong the electrical force really is. And this force is inside every single atom in your body right now, in everything you've ever touched or seen or will ever encounter. So why isn't everything exploding? Why aren't you being torn apart by these tremendous forces? See, all matter, everything, is a mixture of positive protons and negative electrons attracting and repelling with this enormous force. But so perfect is the balance, so incredibly precise is the arrangement, that when you stand near someone else, you don't feel any force at all. The positives and negatives are mixed together so finely, so intimately, that they cancel out almost perfectly. If you have a bunch of positive charges by themselves, they repel each other with tremendous force and spread out in all directions. A bunch of negatives would do exactly the same thing. But if you mix them together evenly, something beautiful happens. The opposite pieces get pulled together by the enormous attractions, and the net result is that these terrific forces balance themselves out almost perfectly by forming tight, fine mixtures of positive and negative. That's what matter is. That's what you are. A perfect balance of enormous forces just sitting there, waiting. You know atoms have a nucleus at the center, right? This heavy, dense core made of protons and neutrons. And around it you have electrons, which are light and carry negative charge. The protons are positive, the electrons are negative. Opposite charges attract. So why don't the electrons just fall straight into the nucleus? Why don't they collapse right onto the protons and stick there? If the electrical force is so tremendously strong, what's keeping them apart? This is where things get genuinely interesting. The answer has nothing to do with electricity at all. It's quantum mechanics. See, there's this principle called the uncertainty principle that says you cannot know both where something is and how fast it's moving at the same time. The more precisely you pin down the position, the more uncertain the momentum becomes. Now, if you try to confine electrons into a very small space, very close to the protons, then according to this principle, they would have to have enormous momentum. They'd have to move incredibly fast. The more you squeeze them in, the more they jiggle around. And that jiggling, that motion required by the laws of quantum mechanics itself, is what keeps the electrical attraction from bringing the charges any closer together. It's like trying to trap something very energetic in a smaller and smaller box. The smaller the box, the more frantically it bounces around. Electrons do exactly this. You squeeze them, they move faster, and that motion keeps them from collapsing into the nucleus. So atoms have this structure, this size, because of a balance between electrical attraction pulling in and quantum mechanical motion pushing out. But now here's where things get really puzzling. What about the nucleus itself? Inside that tiny nucleus you have protons, multiple protons in most atoms, and they're all positive. Positive charges repel positive charges with incredible force, remember? So why don't all those protons just push each other away? Why doesn't every nucleus in the universe simply blow itself apart? Well, it turns out there's another force in nature, a force we don't experience in everyday life. It's called the nuclear force, and it only acts inside the nucleus, only over very, very short distances. And this nuclear force is stronger than the electrical force, strong enough to grab those protons and hold them together despite their electrical repulsion. The nuclear force has a very short range. It falls off incredibly rapidly with distance. The electrical force decreases with the square of the distance, 1 over r squared. But the nuclear force drops off much, much faster than that. So the nuclear force only acts between particles that are practically touching, between each proton or neutron and its immediate neighbors. Meanwhile, the electrical force reaches across the entire nucleus. Every proton repels every other proton, not just its neighbors, all of them. Think about how nature assembles atoms. Hydrogen has just 1 proton, the simplest thing there is. Helium has 2 protons and 2 neutrons, incredibly stable, one of the most tightly bound nuclei you can find. As you move up the periodic table, nuclei get bigger, more protons, more neutrons. And the nuclear force handles everything beautifully because all the particles are close together, all of them within reach of each other's grip. But as you keep adding protons, the nucleus gets bigger. And now you start having protons on opposite sides of the nucleus. They can barely feel each other's nuclear attraction because that force has such short range, but they still feel the full electrical repulsion. The more protons you add, the worse this imbalance gets. The electrical repulsion keeps building up, adding contribution from every single proton, while the nuclear force only connects nearest neighbors. Now, most nuclei find a way to balance this. They add neutrons, which contribute to the nuclear force without adding to the electrical repulsion, since neutrons have no charge. That helps stabilize things. But there's a limit. Eventually, you get nuclei that are so big, with so many protons, that the balance becomes incredibly delicate. The nucleus is holding together, but just barely, like a structure that's been stressed almost to its breaking point. And here's what's remarkable. That delicate balance, that tension between the nuclear force holding things together and the electrical force trying to push things apart, that's where the energy is. That's where the power is hiding. All that electrical repulsion that's being constrained, being held back by the nuclear force, that represents stored energy. Tremendous amounts of energy. See, when you have positive charges pushed close together against their will, it takes energy to keep them there. It's like compressing a spring. The spring wants to expand. It's being held compressed, and that compression stores energy. The nucleus of a heavy atom is exactly like that. All those protons want to fly apart. The nuclear force is holding them together, and that tension, that compression, represents an enormous amount of stored electrical energy. Now, in stable atoms, this energy just sits there. It's locked away, inaccessible, part of the structure of matter itself. You can't get to it through chemistry, through burning things or mixing chemicals, because all of that only involves the electrons on the outside of atoms. The nucleus sits in the center, untouched by ordinary chemistry. That's why chemical energy and nuclear energy are in completely different categories. Chemical reactions rearrange electrons. Nuclear changes involve the nucleus itself, where these enormous forces live. The energy stored in a single nucleus is tiny in absolute terms, but there are astronomical numbers of atoms in any piece of matter. And per atom, per unit of mass, the energy locked in nuclear structure is millions of times greater than the energy available from chemical bonds. That's not an exaggeration. That's the actual ratio. Millions of times more energy hiding inside the nucleus than you can ever access through chemistry. And this is what's so beautiful about understanding atoms. You start with simple ideas. Positive attracts negative. Like charges repel. The nuclear force holds things together at short range. And from just those ingredients, you get all of chemistry, all of matter, and this hidden reservoir of power locked inside every atom. The Empire State Building stands rigid in the wind because electrical forces hold every electron and proton more or less in its proper place. The stiffness of steel, the hardness of diamond, the fact that you don't fall through your chair, all of this is electrical force at work. And it's the same force, the exact same electrical force, that represents such tremendous stored energy inside heavy nuclei. We live our whole lives surrounded by this power, and we never notice it. The balance is so perfect, so complete, that matter just seems solid and stable and boring. You pick up a piece of metal, and it's just a piece of metal. You don't feel the astronomical forces holding every atom together. You don't sense the energy locked inside. Every atom around you is a balance of tremendous forces, a structure held together by the interplay of electricity and quantum mechanics and the nuclear force. And inside that structure is stored the energy that powers stars. The sun doesn't burn like a fire. It doesn't get energy from chemistry. It gets energy from nuclear changes, from that reservoir of power locked inside atomic nuclei. The same physics that makes stars shine, that powers the entire universe, is sitting inside the atoms in your own body right now. Not doing anything, not releasing energy, just sitting there in perfect balance. But it's the same physics, the same forces, the same stored energy. When people first started understanding this in the early 20th century, it was genuinely shocking. Matter, ordinary matter, contains within it energy on a scale that was previously unimaginable. A tiny amount of matter, if you could somehow access that nuclear energy, represents more energy than enormous amounts of chemical fuel. The nuclear force has short range. Heavy nuclei are under tremendous internal stress. That's it. From those simple ideas, you can understand why matter contains such power, why the universe runs on nuclear energy, why stars shine for billions of years. The power hidden inside an atom isn't mysterious or magical. It's the electrical force, the most familiar force in the world. The force that makes lightning and static cling and holds molecules together. It's just that inside the nucleus, this force is compressed, constrained, held in check. And that compression represents energy, enormous energy. Now you might think, okay, I understand there's a lot of energy hidden in atoms, but how does it actually work? What's really happening inside there? And this is where we need to think more carefully about what an atom actually is. See, most people picture an atom like a tiny solar system. You've got the nucleus in the middle, like the sun, and electrons orbiting around it like planets. It's a nice picture, very intuitive, but it's wrong. The electrons aren't orbiting in nice circular pads. They're more like a cloud, a probability cloud, spread out around the nucleus. And they're constantly jiggling, constantly moving, because of that quantum mechanical principle I mentioned. They can't sit still. If they sat still, we'd know exactly where they are and how fast they're moving, which is zero. And that's not allowed. The universe literally forbids it. So electrons have to keep moving. They have to maintain this minimum amount of motion even at absolute zero temperature. Even if you cooled something down as far as physics allows, the electrons would still be jiggling. That's not heat. That's not thermal energy. That's just the quantum mechanical requirement for existence. The universe says you must keep moving, and so they do. Now the nucleus is a completely different story. The nucleus is tiny compared to the atom, incredibly tiny. If you took an atom and magnified it until it was the size of a large room, the nucleus would be a speck you could barely see with your eye. Almost all of the atom is empty space with this diffuse electron cloud. But almost all of the mass is in that tiny speck at the center. Inside that speck, you have protons and neutrons packed together with incredible density. A teaspoon of pure nuclear matter, if you could somehow get it, would weigh millions of tons. That's how tightly packed things are in there. And holding all of that together is the nuclear force, fighting constantly against the electrical repulsion of all those protons. What matters is this balance I keep talking about. The nuclear force attracting, the electrical force repelling, and the structure that emerges from their competition. In small nuclei, the nuclear force wins easily. Helium is incredibly stable, very tightly bound. The 4 particles in there, 2 protons and 2 neutrons, are arranged in a way that's almost perfect. But as nuclei get bigger, something changes. The electrical repulsion keeps adding up, while the nuclear force can only do so much. Think about it this way. If you're a proton sitting in the middle of a large nucleus, you feel the nuclear force from your immediate neighbors, the particles right next to you. But you feel electrical repulsion from every single other proton in the entire nucleus, even the ones far away on the other side. For a small nucleus, this isn't a big deal. There aren't that many protons, and they're all pretty close together. But for a large nucleus, with dozens of protons, the electrical repulsion adds up to something substantial. Each proton is being pushed by all the others, and the nuclear force, strong as it is, only reaches so far. So large nuclei are under stress, internal stress. They're holding together, but there's this constant tension between the force trying to keep things together and the force trying to push things apart. This is why the periodic table ends where it ends. It's not arbitrary. You literally cannot make stable atoms beyond a certain size because the electrical repulsion becomes too much for the nuclear force to handle. The heaviest stable element is lead with 82 protons. Everything heavier than that is unstable to some degree. Take uranium with 92 protons. 92 positive charges, all crammed together, all repelling each other. The nuclear force is holding on, but just barely. The balance is so delicate that the nucleus is almost ready to fly apart from the electrical repulsion alone. Now, what does it mean for a nucleus to fall apart? Well, there are different ways it can happen. Sometimes a nucleus just ejects a small piece of itself, a little cluster of 2 protons and 2 neutrons, which is actually a helium nucleus. This is called alpha decay. The nucleus is too big, too stressed, so it throws out a chunk and becomes smaller and more stable. Sometimes a neutron inside the nucleus transforms into a proton, or vice versa, emitting other particles in the process. This is beta decay. The nucleus is adjusting its composition, trying to find a better balance between protons and neutrons. And sometimes, for very heavy nuclei like uranium, if the nucleus is just tapped lightly, if you send in a slow neutron, just give it a tiny nudge, It can't hold together anymore. It breaks. It splits into two large fragments, each with positive charge. This is fission. And what do positive charges do? They repel with enormous force. So those two fragments fly apart at tremendous speed, pushed by all that electrical energy that was being held in check. And here's the key insight. Medium-sized nuclei are more stable than very large ones. They're in a lower energy state. The protons in a medium-sized nucleus don't feel as much total electrical repulsion because there aren't as many protons to repel them. So when a large nucleus splits into two smaller ones, the final state has less stored energy than the initial state. And that difference in energy has to go somewhere. It goes into motion. The two fragments fly apart at tremendous speed. That's kinetic energy. That's heat. That's the energy release. And here's what's beautiful about this. The energy comes from electricity. It's the electrical repulsion that drives the fragments apart. The nuclear force was holding things together, keeping all that electrical potential energy stored up. And when the nucleus splits, the nuclear force can no longer constrain the electricity. The positive charges push each other away with all that force we talked about at the beginning, and the fragments fly apart. So nuclear energy is really electrical energy. It's the electrical energy that was stored in keeping all those positive charges close together against their will. When you release that constraint, when the nucleus breaks apart, the electrical repulsion converts that stored potential energy into kinetic energy, into motion, into heat. The amount of energy involved is staggering. Each nuclear reaction releases millions of times more energy than a chemical reaction. Millions of times. And this isn't because nuclear forces are somehow magical. It's because the electrical force is so incredibly strong when you're dealing with charges that close together. Inside a nucleus, the distances are tiny, femtometers, millionths of a billionth of a meter. At those distances, the electrical force between protons is enormous. Now, there's another way to get nuclear energy, and it's sort of the opposite of what I just described. Instead of splitting heavy nuclei apart, you can push light nuclei together. This is fusion, and it actually releases even more energy than fission. How does that make sense? If splitting things releases energy, and combining things also releases energy, where's the energy actually coming from? The answer is that middle-sized nuclei are the most stable. Iron, with 26 protons, is about the most tightly bound nucleus you can make. It's at the bottom of the energy valley. So if you start with something heavier than iron and split it, you release energy by moving toward that stable middle. And if you start with something lighter than iron and combine it, you also release energy by moving toward that stable middle. Either way, you're going downhill toward iron.
Fusion is what powers the sun. Hydrogen nuclei, just single protons, are being pushed together so hard that they overcome their electrical repulsion and get close enough for the nuclear force to grab them. And when that happens, when they fuse together, the resulting nucleus is in a lower energy state than the separate particles were. That difference in energy is released as light and heat. The sun is converting hydrogen into helium, moving from the lightest elements toward that stable middle and releasing energy in the process. It's been doing this for about 5 billion years, and it'll keep doing it for another 5 billion before it runs out of hydrogen fuel. That's how much energy is stored in those light nuclei, enough to power a star for billions of years. And the elements heavier than iron, where do they come from? They actually require energy input to create. They're made in supernova explosions when dying stars release so much energy that they can push nuclei past iron up the energy hill rather than down. Every atom of gold or uranium in the universe was created in the violent death of a star. So the energy hidden in atoms connects to everything. It's why stars shine, why the sun warms the earth, where the elements came from. All of it traces back to this balance of forces inside the nucleus. This tension between electricity trying to push things apart and nuclear force trying to hold things together. The thing that gets me about all of this is how ordinary it seems from the outside. You look at a piece of metal, a rock, a glass of water, and it just sits there, completely still, completely boring. But inside, at every moment, there's this incredible drama playing out. Forces pushing and pulling, particles jiggling, energy stored and balanced with such precision that the whole thing appears motionless. And the numbers involved are just staggering. A single gram of matter contains something like 1 trillion atoms. Each one of those atoms has a nucleus, holding protons together against their electrical repulsion. Each one has electrons maintaining their quantum mechanical dance around the outside. And all of it is happening right now, constantly, everywhere, in everything. That's the thing about nuclear energy. It's isolated from everyday physics. Chemical reactions shuffle electrons around. Heat makes atoms jiggle faster. But the nucleus just sits in the center of it all, completely indifferent. It takes something much more dramatic to affect what's happening in there. You need particles with enough energy to actually penetrate to the nucleus. This is why nuclear physics was discovered so late in the history of science. Electricity was understood in the 1800s. Chemistry was well developed. But nuclear physics had to wait until the 20th century because you need special tools to probe something that small and that well protected. The first hint that something was going on inside atoms came from radioactivity. People noticed that certain materials emitted invisible rays that could fog photographic plates and make air conduct electricity. This was completely mysterious at first. Where was this energy coming from? The materials weren't connected to anything. They weren't being heated or stimulated. They were just sitting in a drawer, emitting energy year after year. It took decades to figure out that the energy was coming from inside the atoms themselves. The nuclei of certain elements were unstable, and occasionally one would transform, releasing a burst of energy in the process. Not chemical energy, something else entirely. Something from deeper inside the atom than anyone had previously imagined. And when people finally understood what was happening, when they realized how much energy was stored in nuclear structure, it changed everything. Ordinary stuff, the rocks and metals and water we'd been living with forever, turned out to contain power on a scale that was previously unimaginable. A single kilogram of matter, if you could convert all of its mass to energy, contains the equivalent of millions of tons of chemical fuel. Millions of tons from 1 kilogram. Now, you can't actually convert all the mass to energy through nuclear reactions. You only release a tiny fraction of the total. But even that tiny fraction is enormous compared to anything chemistry can provide.
Every child learns their first language without a single grammar lesson. They don't memorize verb conjugations or study vocabulary lists. Yet by age 5, they speak fluently. Something profound happens in those early years that most language courses completely miss. When people sit down to learn a new language as adults, they typically reach for a textbook. They start memorizing words. They study conjugation tables. They practice grammar drills. And after months or even years of this, they still can't hold a basic conversation. Why? Because they're trying to build a house by memorizing the names of all the tools instead of actually building. The brain doesn't learn languages the way textbooks teach them. Understanding this difference changes everything. Consider what happens when someone opens a language textbook. The first chapter usually presents a list of common phrases. Hello, goodbye, my name is, where is the bathroom? The student dutifully writes these down, repeats them, tries to commit them to memory. Then they move to chapter 2, which introduces new phrases and perhaps some basic grammar rules. The pattern continues. Memorize, drill, test, move forward. This approach treats language like a collection of facts to be stored. But language isn't a collection of anything. It's a living system, a way of thinking, a method the brain uses to represent reality. You can't memorize your way into a system any more than you can memorize your way into understanding how a car engine works just by learning the names of all its parts. The fundamental mistake people make is confusing knowledge about a language with the ability to use it. These are completely different things. You can know every grammar rule in Spanish and still freeze when someone asks you a simple question in a cafe. Knowledge sits in one part of the brain. Ability lives somewhere else entirely. So how does the brain actually acquire language? Look again at that 5-year-old child. They don't know what a verb is. They couldn't explain subject-verb agreement. Yet they use language correctly, naturally, without thinking. How? The child does something that seems almost too simple to be powerful. They play with the language. They hear sounds, they try to make those sounds, they notice what happens. They don't ask, what's the rule? They ask, what happens if I say it this way? They experiment, they fail, they adjust, they try again. And gradually, through thousands of these little experiments, the brain builds an intuition for how the language works. This is the key that unlocks everything. Intuition, not memorization. Here's the method, and it works because it aligns with how the brain naturally processes language. Take any piece of writing in the language you're learning. It doesn't matter if it's a children's book, a newspaper article, or a technical manual. Choose something you're genuinely curious about. This matters more than you might think. The brain pays attention to what interests it and largely ignores what doesn't. Now, don't do what most people do. Don't look up every word you don't know. Don't study the grammar. Instead, do this. Read it and try to guess what it means. Not a wild guess, but an informed guess, based on whatever you can figure out. Maybe you recognize a few words. Maybe the context gives you clues. Maybe you can see patterns in how words connect to each other. Use all of it. Then, and this is crucial, check if you were right. Find a translation or ask someone who knows the language. But here's where it gets interesting. You're not checking to memorize the correct answer. You're checking to see if your mental model works. When you guess wrong, your brain notices the gap between what you expected and what's actually true. That gap is pure gold. That's where learning happens. The brain is a prediction machine. It's constantly trying to anticipate what comes next, what things mean, how patterns work. When your prediction is wrong, the brain updates its model. It adjusts. It learns. But this only happens if you make predictions first. If you just look up the answer without guessing, the brain has nothing to update. The information slides in and slides right back out. This is why memorizing vocabulary lists feels so futile. You're feeding the brain answers to questions it never asked. There's no prediction, no gap, no learning mechanism engaged. The words sit in short-term memory for a while, then evaporate. But when you struggle to figure out what a sentence means, when you wrestle with it, when you form a hypothesis and then test it, you're engaging the same mechanism that 5-year-old uses. You're building intuition. Let's go deeper into what this means. Every language has its own internal logic, its own way of carving up reality. In English, we say, I am cold. In Spanish, they say tengo frío, which literally translates to I have coldness. That's not just a different way of saying the same thing. It's a different way of thinking about the experience of being cold. You own the coldness rather than being it. When you memorize that tengo frío means I am cold, you learn a translation, but you don't learn the logic. You don't develop an intuition for how Spanish thinks about states of being versus possession. The translation is a bridge, but it's a bridge you're supposed to cross and then leave behind. Here's what happens when you use the prediction method instead. You encounter tengo frío in a sentence. You know, tengo has something to do with having. You've seen frío before, maybe connected to ice or winter. You think, I have cold? Maybe it means I feel cold? You check. You're right. Your brain notices, Spanish uses possession for internal states that English treats as being. The next time you encounter this pattern, maybe with tengo hambre for I am hungry, you don't need to look it up. Your brain predicts. If cold is having, hunger probably works the same way. You check. Correct again. The pattern strengthens. You're not memorizing translations anymore. You're developing a feel for how the language thinks. This is the difference between learning vocabulary and learning language. Vocabulary is a list. Language is a system. Systems can't be memorized. They have to be felt, discovered, intuited. But there's another layer to this that makes it even more powerful. After you've read something and checked your understanding, do this. Explain it to yourself out loud in the target language as if you're teaching it to someone else. Don't just repeat what you read. Rephrase it. Use your own words, even if they're clumsy. Try to express the same idea in a different way. Why does this work? Because explaining something forces you to truly understand it. When you just read or listen, your brain can be lazy. It can nod along, creating the illusion of understanding without really processing deeply. But when you have to explain something, you can't fake it. The gaps in your understanding become immediately obvious. Plus, speaking activates different neural pathways than reading. You're not just recognizing patterns anymore. You're producing them. The brain has to actively construct sentences, choose words, apply patterns. This builds the actual machinery of language use, not just the ability to recognize it. Think about what happens in that moment when you're trying to explain something in the new language. You want to say a particular thing, but you don't know the exact words, so you have to work around it. You have to find another way to express the same idea using the limited vocabulary you have. This is exactly what fluent speakers do all the time. They don't know every word either. They know how to navigate around gaps, how to use what they have to get where they want to go. Every time you struggle to express an idea and find a way through, you're strengthening that navigational ability. You're teaching your brain that language is flexible, that there are multiple paths to any destination. This is the opposite of the textbook approach, which implies there's one right way to say everything. Here's something else that happens with this method. You start to develop a relationship with ambiguity. Most language learning materials try to eliminate ambiguity. Everything is clear, defined, explained, but real language is full of ambiguity. Words have multiple meanings. Context matters. Nuance exists. When you're guessing at meaning, you're sitting with ambiguity. You're developing comfort with not knowing exactly, with having a general sense rather than a precise definition. This is how native speakers experience their own language. They don't have dictionary definitions in their heads. They have fuzzy, context-dependent intuitions. A native Spanish speaker doesn't think tengo frío means I am cold. They hear tengo frío and directly feel the concept of coldness, no translation required. That directness, that immediate connection between sound and meaning, is what you're building when you work with intuition instead of memorization. The speed of this matters too. 15 minutes might seem impossibly short for meaningful language learning, but that's because most people spend those 15 minutes inefficiently. They read a page, look up 10 words, forget 9 of them, and repeat. Exhausting and futile. Instead, take one paragraph, just one, spend 15 minutes with it, but spend those minutes intensely. Read it, guess at every unknown word and phrase. Check yourself, read it again, noticing what you missed the first time. Explain it out loud in your own words. Try to write a similar paragraph about something else. Play with the structures you found, rearrange them, see what breaks and what works. 15 minutes of this kind of active, playful engagement builds more real language ability than an hour of passive vocabulary memorization. Why? Because you're not trying to add information to your brain, you're trying to change how your brain works. You're building new neural pathways, new ways of thinking. That happens through doing, through struggling, through playing, not through memorizing. This is also why children learn so much faster than adults. Even though adults theoretically have better study skills and more discipline, children are willing to sound stupid. They babble. They make mistakes constantly. They don't care. Adults want to be correct before they speak, so they study rules and memorize phrases, hoping to achieve correctness before attempting production. But the brain learns by doing, not by preparing to do. There's a deeper principle at work here, one that applies far beyond language learning. The brain is not a storage device. It's a pattern recognition and pattern generation system. It learns by finding regularities in experience, by building models that predict what will happen, by adjusting those models when predictions fail. Every time you encounter something that surprises you, something that doesn't fit your current model, your brain has a choice. It can dismiss the anomaly, or it can update the model. Active engagement, the kind where you make predictions and test them, forces the brain to update. Passive reception, like listening to a lecture or reading a textbook, lets the brain stay comfortable with its current model. This is why explaining things to yourself matters so much. When you try to use a pattern you think you've learned, you discover whether you actually understand it. If you can't use it, you don't really know it yet. The attempt to use it reveals the gaps, and revelation of gaps is the first step toward filling them. Now, what does this look like in practice? Imagine sitting down with a simple book in French. You've been learning French for a month using this method. You open to a new page. There's a sentence, Le chat dort sur le canapé. You know, le chat is the cat. You've seen dort before, connected to sleeping. Sur means on. Le canapé is new, but context suggests furniture. You guess, The cat sleeps on the couch. You check. Correct. But notice what else you just learned without trying. Eli is used for both masculine nouns. You've now seen it with chat and canapé. The pattern strengthens. Next sentence. Il rêve de souris. Il is he or it. Rêve is new. De means of. Souris, you don't know. But you have a cat sleeping, so probably dreaming. Of what? What do cats dream of? You guess, he dreams of mice. You check. Right. And you've just learned rêve in context, connected to an image, tied to meaning, not just as a word on a vocabulary list. This is playful. This is active. This is how children learn, and it's how adults can learn if they set aside the belief that learning must be serious, structured, and systematic. The most important shift is internal. Stop trying to learn French or Spanish or Japanese. Instead, start trying to think in French, to think in Spanish, to think in Japanese. Even if you only know 20 words, use those 20 words to think. When you see a dog on the street, try to think dog in the target language. When you're hungry, think I am hungry in the target language, even if you have to look up the phrase first. This constant low-level engagement does more than any formal study session because it integrates the language into your actual thinking process. Language isn't something separate that you pull out when needed. It's the substrate of thought itself. When you use it to think, even in small ways, you're building that substrate. Here's the truth that textbooks won't tell you. You don't need to know many words to start using a language meaningfully. You need to know how to use the words you have. A child with a 300-word vocabulary can express an enormous range of ideas because they know how to play with those words, how to combine them, how to use context and gesture and tone. An adult with a 3,000-word vocabulary often can't say anything because they learned those words as isolated facts, not as tools for thinking. They know what the words mean in English, but they don't know how to use them, how they fit together, what patterns they form. This method fixes that. Every prediction you make, every guess you test, every explanation you construct, you're learning how to use the language, not just what it means. You're building the doing, not just the knowing. And here's what happens over time. The language starts to feel different. At first, every sentence is a puzzle you have to consciously solve, but gradually, some things start to feel automatic. You see a sentence structure you've encountered before, and you understand it immediately, no translation required. You want to express an idea, and a phrase appears in your mind in the target language, not English. These moments of directness, where the language connects straight to meaning without passing through translation, are small victories. Each one represents a piece of real language ability. String enough of them together, and you have fluency. The path isn't memorizing 10,000 vocabulary words and all the grammar rules. The path is using what you know, however little, to engage with the language as a living system. Make predictions, test them, speak even when you're uncertain. Explain things to yourself, play with structures, notice patterns, adjust your mental model when it fails. 15 minutes a day of this kind of engagement will take you further than an hour of memorization because you're building the right thing. You're not building a database of facts about a language. You're building the ability to use language, to think in it, to let it become part of how your mind works. This is what the brain wants to do. The brain is built for language. Every healthy human brain acquires language naturally when given the right kind of exposure and interaction. The problem isn't that adult brains can't learn languages. The problem is that adults use methods that fight against how the brain naturally works. Stop fighting, start playing, make guesses, be wrong, adjust. Try again, speak badly, explain clumsily, notice patterns, use context, build intuition. The language will come, not because you memorized it, but because you lived it, even just 15 minutes at a time. That's the real trick. Not some magic technique, but simple alignment with how learning actually happens. The brain is ready. It's been ready all along. You just have to give it what it needs. Active engagement, prediction and testing, playful exploration, and permission to be wrong on the way to being right.
As soon as you learn something, the biggest trap is keeping it to yourself.
believing you've understood. But the human mind loves to deceive itself. It creates the illusion of knowing when in fact it only memorized. The genius discovers the opposite trick. Teach immediately. When you explain something out loud as if you were teaching a child, your brain is forced to organize your thoughts, to separate what you truly understand from what's still vague. Imagine your brain as a muscle. Every time you receive information, it's like lifting a small weight. But here's the truth that changes everything. You don't get stronger by lifting once. You only build strength when you repeat, when you apply, when you test that muscle in different situations. And that's where Richard Feynman's secret comes in, the power of teaching in order to learn. There's a shocking secret about your mind that almost no one dares to reveal. Not because it's too complicated, but because it's too simple. And simplicity has always been the territory of geniuses. Pay close attention to me now, because if you grasp what I'm about to tell you, you will never see learning the same way again. How many times have you read or heard something that seemed clear, but when you tried to explain it, you realized you couldn't? That's not failure. That's a signal. It's your brain exposing the weak points in your understanding. And it's precisely in the act of trying to explain that you strengthen your grasp. It's as if your mind said, now I really need to understand this because I have to make it simple for someone else. This is the secret workshop of geniuses. They don't just keep knowledge, they transform it into clarity. And here's the key. Real learning doesn't happen when you read, listen, or it happens when you translate it into your own words. That's the moment when the mind stops being a spectator and becomes a creator. And when the mind creates, it awakens abilities that were once asleep. Picture yourself doing this starting today. You read a powerful idea, and instead of rushing to the next one, you explain it. You step into the role of a teacher, even if your only student is yourself in front of the mirror. This may sound simple, but it's exactly the kind of simplicity that separates ordinary mind from extraordinary one. Imagine you just learned a powerful idea about discipline. Instead of just thinking, I get it, you stand up and say out loud, discipline is like a muscle. The more you train it, the stronger it gets. Suddenly you've created an image that wasn't in the text but was born from you. And that act of creation burns the knowledge into your mind like a tattoo. Now I want you to understand what this really means in practice. Every time you learn something new, do 3 simple things. First, explain it out loud as if you were teaching someone who has never heard of the subject before. Second, if you stumble over your words or realize you can't simplify it, go back and study that point again until you can. Third, use everyday examples. If it's a concept about focus, compare it to holding a lens that concentrates light into a single point until fire appears. The simpler and more visual, the more powerful the learning becomes. And don't stop there. There's another almost magical trick. Write it down. Writing forces the brain to slow down, to organize, and to give shape to what you've understood. Writing is like building a bridge between your mind and the physical world. And when you later read what you wrote, you're looking at your own thoughts from the outside, like an engineer inspecting his own structure. This sharpens clarity and strengthens memory in a way that's truly remarkable. Most people never do this. They consume information the way they eat fast food. They swallow it, but don't absorb it. The result? They live full of data, but empty of understanding. Geniuses don't do that. A genius chews slowly, digests, transforms. They explain, they write, they repeat, until each concept becomes part of their identity. And here's the reflection you must keep in your mind. Learning is not about accumulation, it's about transformation. Every time you teach what you just learned, you're not only reinforcing your memory, you're also creating new doors inside your mind. Doors that lead to insights, creative solutions, and ideas that were hidden before. That is the true unlocking of brain power. Now imagine with me something that could completely change the way you learn. Sitting in front of a book or an idea and diving so deeply that the world around you disappears. This is the state of focus Richard Feynman pursued. He believed that learning is not about keeping your eyes on words, but about putting your whole mind inside the concept. Pay close attention now, because here is one of the greatest secrets of focus: eliminating the excess. The mind was not designed to carry 1,000 things at once. When you try to learn while thinking about text messages, bills to pay, and daily worries, your energy fragments. It's like trying to light a fire with 10 matches in the wind. Nothing catches. But when you protect a single match, it becomes a flame. And from that flame, the fire is born. Focus is exactly that. protecting your attention from everything else until it becomes a flame strong enough to illuminate and engrave knowledge into your mind. One practical technique you can apply immediately is the concentration notebook. Feynman used to take notes not just to record information, but to clear out mental noise. By writing a clear question at the top of the page, what does this concept really mean? He forced his brain to align in a single direction. All mental energy was guided toward answering that one question. That's what gives depth to learning. Another powerful secret is turning curiosity into fuel. When you learn something only out of obligation, your mind resists. But when you turn it into a game, a challenge, real curiosity, focus lights up on its own. Ask yourself, what does this have to do with the real world? How can I use this idea in a practical way? These questions are like magnets that pull your mind back every time it tries to escape. And remember, focus is not rigidity, it's flow. When you enter this state, you don't feel time passing. You're not fighting distractions. You're simply so absorbed that nothing else matters. That is true deep learning. That is what transforms information into wisdom. Picture yourself applying this today. Instead of just opening a book, you open a portal. You decide that for the next few minutes, nothing exists except the idea in front of you. Each line you read, each word you explain, each example you write is a step deeper into a new universe. This is the experience that awakens the genius already inside you. Now understand this once and for all. The difference between an ordinary mind and a genius mind is not IQ. It's not secret gifts. It's how you train your brain every single day. Teaching in order to learn, writing to organize, focusing with intensity, and giving yourself fully to knowledge. Imagine the power of applying this in your own life. You don't just learn faster, you start to think with clarity, to create solutions others can't see, and to turn every idea into action. This is the state of mental greatness that Feynman lived by, and it's the state you can live too, if you choose to apply it. And here's my final request. Don't let this knowledge pass by like just another video you watch and forget. Write right now in the comments, "I will unlock my brain," to affirm this commitment to yourself. That simple act will anchor in your mind the decision to take action. If this video made sense to you, hit the like button right now because it shows you're on the right path. Subscribe to the channel and turn on the notifications because here you'll find more secrets and lessons to expand your mind and live at the highest level of your potential. Remember, the mind doesn't expand on its own, it expands when you act. This is the moment to act. And if you've made it this far, you've already proven you're ready to go further. A real one. Not a scam, not a hack, not some productivity trick that stops working after a week. A genuine shortcut that actually works, that compounds over time. That made Richard Feynman one of the most successful minds in history. Our paws lean in Feynman, and nobody warned you about it. Not your teachers, not your professors, not your mentors, not the self-help gurus. No, why? Because this shortcut looks like the opposite of success. It looks like failure. It looks like wasted time. It looks like you're going in the wrong direction. So everyone avoids it. Everyone takes the long, hard road instead. And they wonder why success is so difficult. Why they're working so hard and getting nowhere. Why other people seem to have some secret they don't know. A direct statement, well, I'm going to tell you the secret. Right now, right here. And I'm warning you, when you hear it, you're not going to believe me. You're going to think it's too simple, too obvious, too counterintuitive to actually work. But it does work. It worked for Feynman. It's worked for every genuinely successful person I've studied. And it'll work for you too. If you're willing to take it, if you're willing to look foolish for a while, if you're willing to do what everyone else refuses to do. Ready? Here it is. Apri pause for dramatic effect. The shortcut is admitting you don't know. Etcher, let that land. Watch the confusion. I told you. You don't believe me. You're thinking, that's not a shortcut. That's just being honest. That's not going to make me successful. But you're wrong. And I'm going to prove it to you. With stories, with logic, with Feynman's entire life as evidence. By the time we're done here, you're going to understand why the fastest path to mastery is admitting ignorance. Why the quickest road to expertise is confessing confusion. Why the shortcut everyone avoids is the only one that actually works. Let me show you what I mean. So tell this story with building intensity. It's 1943. Feynman is at Princeton. He's young, 25 years old, working on his PhD, and he's invited to his first major physics conference. All the big names are there, the legends, the people who write the textbooks, and there's a presentation. One of the famous physicists is explaining his latest work, complex stuff, cutting-edge research. Everyone's listening intently. Everyone's nodding along. These are the smartest people in physics, and they all seem to understand. The presentation ends. The moderator asks, "Any questions?" Silence. Nobody wants to look stupid by asking a question. Nobody wants to admit they didn't understand. These are supposed to be the experts. They're supposed to know this stuff. I pause, and then Feynman raises his hand. "I don't understand what you just said." The room freezes. Everyone turns to look at him, because Feynman just did the unthinkable. He admitted ignorance. In front of everyone, in front of the legends, in front of his peers. And you know what the presenter says? "Oh, let me explain it differently." And he does. He uses a different approach. Simpler terms, better examples. Build this and suddenly 3 other people raise their hands. "I didn't understand either." Then 5 more. Then 10. Turns out almost nobody in that room understood the presentation. They were all faking it, all pretending, all protecting their reputations. Except Feynman. They'd make the pointer. And here's what happened over the next few decades. All those people who pretended to understand, most of them faded into obscurity. They played it safe. They protected their images. And they never really learned anything. Feynman. He became one of the greatest physicists of the 20th century. Nobel Prize. Revolutionary discoveries. Legendary insights. Not because he was smarter, but because he took the shortcut. He admitted what he didn't know. And that admission gave him permission to actually learn it. Hard walk across stage. This is the shortcut nobody warned you about. And it's counterintuitive as hell. Because everything in our society teaches us the opposite. Everything tells us to fake it, to appear confident, to never admit weakness, to always look like we know what we're doing. Fake it till you make it, they say. Act like you belong. Never let them see you sweat. Project confidence even when you're unsure. Get intensus. And you know what happens when you follow that advice? You get really good at faking it. You get really good at appearing confident. You get really good at looking like you know what you're doing. But you never actually learn. You never actually improve. You never actually become competent. You're spending all your energy maintaining the appearance of knowledge instead of acquiring actual knowledge. I sure pause. That's the long road. The hard road. The road everyone's on, working hard to look successful instead of working smart to become successful. The shortcut. Admit you don't know. Stop faking. Start learning. Let me show you how powerful this is with another story. Share this example. A Feynman gets invited to join the Manhattan Project. The atomic bomb. He's one of the youngest people there, and he's surrounded by legends. Niels Bohr, Robert Oppenheimer, Enrico Fermi, the people who invented quantum mechanics, the giants of physics. And in the meetings, these giants are discussing complex problems. Really complex. The kind of stuff that determines whether the bomb will work or kill everyone trying to build it. And Feynman doesn't understand something. Some calculation, some assumption, some approach. Most young physicists would stay quiet. You don't interrupt Niels Bohr. You don't question Enrico Fermi. You nod along. You pretend you get it. You figure it out later. Shears slow down here, not Feynman. He raises his hand and he says, "I don't understand why we're doing it this way. Can someone explain?" And Bohr looks at him. And instead of being annoyed, he's delighted. Because finally, someone is asking real questions instead of pretending. Bohr starts explaining. And Feynman asks follow-up questions. And they have a real conversation. A genuine exploration of the problem. Build the payoff, and from that conversation, they discover an error in their approach. A mistake that could have been catastrophic. That nobody caught because everyone was too busy pretending to understand to actually think critically. Feynman's willingness to admit ignorance saved the project. Make the point, and here's what's crucial. Bohr specifically asked to work with Feynman after that. He wanted the young guy who asked questions, not the experienced guys who pretended to know everything. Because Bohr understood the shortcut. He understood that the person willing to admit ignorance is the person who actually learns, who actually grows, who actually becomes valuable. A direct address. I know what you're thinking. But if I admit I don't know things, people will think I'm stupid. They won't respect me. I'll lose opportunities. And I get it. That fear is real. The fear of looking incompetent. The fear of being judged. The fear of losing credibility. But here's what actually happens. Let me tell you about my own experience with this shortcut. Before I get personal, I used to fake it constantly. In meetings, I'd nod along even when I was lost. In conversations, I'd use jargon to hide my confusion. When learning new things, I'd pretend I understood so I could move on quickly. And you know what? I was stuck. For years, I was working hard. I was busy. But I wasn't growing. I wasn't improving. I wasn't becoming more capable. Because I was spending all my energy maintaining the illusion of competence instead of building actual competence. Most share the turning point. Then I read about Feynman, and I decided to try the shortcut, to start admitting when I didn't understand things. And at first, it was terrifying. I'm in a meeting. Someone's explaining a strategy. I don't get it. And instead of nodding along, I say, I don't understand. Can you explain that differently? Everyone looks at me. I feel like an idiot. But then the person explains it again, more clearly, and I actually understand. And then someone else says, oh, I was confused about that too. Thanks for asking. Build this he. And over the next few months, something amazing happened. People started coming to me with questions. People started valuing my input more. People started seeing me as someone who actually understood things, not just someone who parroted what they'd heard. Why? Because I'd stopped faking. I'd stopped pretending. And because of that, when I did say I understood something, people believed me. They knew I wasn't just nodding along. They knew I'd actually figured it out. Fate pausa, that's the paradox of the shortcut. When you admit what you don't know, people trust you more about what you do know. When you fake everything, people trust you about nothing. I'll walk to other side of stage. Let me break down exactly why this shortcut works. Why admitting ignorance is actually the fastest path to success. Because it's not just about honesty. It's not just about humility. There's a deeper mechanism at play here. A fixture explained this clearly. When you admit you don't know something, three things happen. First, you stop wasting energy on pretense. All that mental effort you were using to maintain the illusion of knowledge, that gets freed up. You can use it for actual learning instead. Think about how exhausting it is to fake understanding, to keep track of what you're supposed to know, to avoid situations where your ignorance might be exposed, to maintain the facade. Actus gesture, that's a massive cognitive load, and it's constant, and it prevents you from actually engaging with the material, because you're too busy managing appearances to actually learn. When you admit ignorance, that load disappears. Suddenly, all that energy is available for learning, for thinking, for understanding. Second, you get targeted help. When you admit what you don't know, people can help you with exactly what you need. But when you pretend to understand everything, people assume you're fine. They don't offer help. They don't explain further. They don't provide the resources you need. Give example. Imagine you're learning something complex, let's say coding, and you pretend you understand classes and objects and inheritance. Your teacher moves on. Your colleagues assume you've got it. Nobody offers additional explanation or resources. But you don't actually understand. So when you try to apply it, you struggle. You waste hours trying to figure it out alone. You make mistakes. You get frustrated. That contrast to now imagine you admit, I don't understand classes and objects yet. Suddenly, your teacher spends extra time explaining. Your colleagues share resources that help them. Someone offers to pair program with you. You get targeted help exactly where you need it. And you learn in hours what would have taken days to figure out alone. Third, you build real understanding instead of surface knowledge. This is the biggest one. When you pretend to understand, you move on before you're ready. You build on shaky foundations. You accumulate surface knowledge without deep understanding. And eventually it all falls apart. When you need to apply that knowledge to something new, you can't. Because you never really understood it in the first place. Or make it concrete. But when you admit ignorance and stay with something until you truly understand it, you build solid foundations. Real understanding. The kind that transfers. The kind that compounds. The kind that makes you genuinely capable. That's why it's a shortcut. Not because it's faster in the moment, but because you only have to learn something once. You learn it properly. You don't have to come back and relearn it later when your fake understanding fails you. The people who fake it, they have to learn the same thing multiple times because they never really learned it the first time. That's the long road. The people who admit ignorance and learn properly, they learn it once and move on. That's the shortcut. Tell this story. Let me give you a Feynman example that makes this crystal clear. Feynman is teaching undergraduate physics at Caltech, and he notices something. The students can solve the problems, they can pass the tests, they can recite the equations, but they don't actually understand physics. So he does something radical. He changes how he teaches. Instead of lecturing on what they should know, he starts asking what they don't understand. Asak share this, he says to them, I'm not going to pretend you understand things you don't, and I'm not going to let you pretend either. If you don't understand something, say so, out loud, in class, in front of everyone. The students are uncomfortable at first. Nobody wants to be the one who doesn't get it. But then someone admits, I don't understand why energy is conserved. And Feynman lights up. Excellent! That's the most important question you could ask. Let's explore it, and to continue the story. And he doesn't just give them the answer. He explores it with them. He shows them how to think about it. He admits when even he doesn't fully understand aspects of it. And something magical happens. The students start actually understanding physics, not just passing tests. Understanding, because they stopped pretending. They started admitting what they didn't know. And that admission gave them permission to actually learn it. Make the points of Feynman's lectures from that period became legendary. They're still studied today. Why? Not because he made physics easier, but because he made understanding possible. By normalizing ignorance, by making it safe to admit what you don't know. By showing that admission isn't failure, it's the first step towards success. But get practical. So how do you actually use this shortcut? How do you start admitting ignorance in a way that accelerates your success instead of hurting it? Because I know there's a fear here. I know you're worried about doing this wrong, about looking stupid, about damaging your reputation. Let me give you the framework, the way to use this shortcut effectively. Let's present this clearly. First, be specific about what you don't know. Don't just say, I don't understand. That's too vague. That makes you look lazy. Instead say, I understand A and B, but I'm confused about how C connects to them. Can you clarify that connection? Aaron can explain C the difference. The second version shows you've engaged with the material. You've thought about it. You're asking a genuine, specific question. That doesn't make you look stupid. That makes you look engaged, thoughtful, serious about learning. Was there a second point? Second, ask questions that move understanding forward. Don't ask questions just to hear yourself talk. Don't ask questions you could easily Google. Ask questions that get at real understanding, that probe the logic, that test the assumptions. Why does this work? What would happen if we change this variable? How does this connect to that other concept we discussed? Give example, Lee. These are the questions Feynman asked constantly. Not what is the answer, but why does this work? Not what should I memorize, but what's actually happening here. These questions demonstrate thought. They show you're trying to understand deeply, not just memorize superficially. Third, admit ignorance confidently. This sounds paradoxical, but it's crucial. Don't apologize for not knowing. Don't be sheepish. Don't act like ignorance is a character flaw. Say it confidently. I don't understand this yet. Help me understand it. Or explain the difference. C. I'm sorry. I'm probably just being stupid, but I don't think I get this. That's weak. That's apologizing for learning. Versus, I don't understand this yet. Let's break it down. What's actually happening here? That's confident. That's taking ownership of your learning. Make the point. Feynman never apologized for not knowing things. He was curious about them. He was interested in them. He wanted to understand them. That wasn't weakness. That was strength. And people responded to that strength. They respected it. They wanted to help him. A fourth point. Show what you've tried. When you admit you don't understand something, show that you've engaged with it, that you've thought about it, that you're not just being lazy. I've read this section 3 times and I think I understand X and Y, but Z doesn't make sense to me. Here's what I think might be happening, but I'm not sure. Can you clarify? Explain. That's not just admitting ignorance. That's showing effort. That's showing you're using ignorance as a starting point for learning, not as an excuse for not trying. And people respect that. They want to help people who are trying. They don't want to help people who want to be spoon-fed. A pause, bring it together. So that's the framework. Be specific, ask forward-moving questions, admit confidently, show your work, do those 4 things, and admitting ignorance becomes a superpower. It becomes the shortcut to success that it actually is. All right, tell one more story. Let me give you one final Feynman story that encapsulates all of this. It's late in his career. Feynman is famous, Nobel Prize winner, legendary physicist, and he's invited to give a talk at a major conference. And he starts his talk by saying, I'm going to tell you about something I don't understand. Let that land on not something I've figured out. Not something I'm an expert in. Something he doesn't understand. And then he spends 45 minutes exploring this problem he can't solve, showing what he's tried, explaining where he gets stuck, admitting what confuses him. The audience is captivated because they're watching a genius think, not recite. Think, struggle, wonder. Avatara continue. And at the end, someone in the audience suggests an approach Feynman hadn't considered, and Feynman's eyes light up. That's interesting. I hadn't thought of it that way. Let me explore that. Right there, in front of everyone, he admits he hadn't thought of something. He doesn't pretend he had. He doesn't save face. He learns. And you know what everyone said afterward? That it was the best talk they'd ever seen. Not because Feynman had all the answers, but because he showed them how to think, how to question, how to learn, by admitting what he didn't know. Walk to center stage. So here's what I want you to understand. Really understand, success isn't about knowing everything. It's not about having all the answers. It's not about appearing competent. Success is about learning faster than everyone else, about understanding deeper than everyone else, about growing more than everyone else. Make the connection. And the shortcut to that, the real shortcut, the one that actually works, is admitting what you don't know. Because admission is the first step of learning. You can't learn something if you're pretending you already know it. You can't grow if you're maintaining the illusion that you don't need to. Get passionate. The people who fake it, they're stuck. They're trapped in their current level of knowledge. They're working hard to appear successful instead of working smart to become successful. The people who admit ignorance, they're free. They're learning constantly. They're growing continuously. They're actually becoming more capable every single day. Some point, that's the shortcut. That's the secret. That's what nobody warned you about. Admit you don't know, then learn it properly, deeply, once. That's faster than pretending you know and never really learning it. That's faster than fake understanding that collapses under pressure. That's faster than surface knowledge that doesn't transfer. Final challenges. So here's what I want you to do, starting today. Right now, find one thing you've been pretending to understand. One concept, one skill, one area of knowledge where you've been nodding along but secretly confused. And admit it to yourself first, then to someone who can help you learn it. Pause and say it out loud. I don't actually understand this. I've been pretending. Can you help me really learn it? And then actually learn it. Don't just get a surface explanation and move on. Stay with it until you truly understand, until you could explain it to someone else, until you've built real knowledge. Build to conclusion and do that once. Just once. And notice how different it feels. How much faster you learn when you're not maintaining the illusion of knowledge. How much more confident you feel when your understanding is real instead of fake. And then do it again and again. Make it a habit. Make it your default. Stop faking. Start admitting, slow down. That's what Feynman did. Every single day of his life, he admitted what he didn't know. He asked the questions everyone else was afraid to ask. He learned what everyone else pretended to already understand. And that made all the difference. Not talent, not intelligence, not luck. The willingness to admit ignorance. To look foolish temporarily so he could become wise permanently. To take the shortcut everyone else avoided because they were too proud or too scared. Final statement. You can take that shortcut too. You can stop faking. You can start learning. You can grow faster than you ever thought possible. But only if you're willing to do what Feynman did. What all genuinely successful people do. Admit you don't know. That's the shortcut. That's the secret. That's what nobody warned you about. Pause it now! You know, the question is, will you use it? Thank you! And if you want more insights into how Feynman actually thought and worked, if you want more shortcuts, more techniques, more secrets that genuinely accelerate success, do me a favor, like this video and subscribe to the Mind of Richard Feynman channel. We're uncovering the real methods behind one of history's greatest minds with practical applications you can use immediately. Join us. Let's take the shortcuts that actually work. See you in the next one.